and thanks to both the Alexes. I was first here as a postdoc in '87, and I asked Alex for a letter of support actually at that time. So clearly it worked, so thank you. And thanks to the other Alex for his help. So my brief, as I understand it, was to give an introduction to arithmetic groups and also to monodromy groups before going on to state the computations of certain arithmetic monodromy groups. So let me, this is going to be really elementary, this talk. I hope you will excuse me because as I understood, I thought I should define whatever it was that I was going to use. So let me start with a linear algebraic group. G in GLN is a subgroup which is the set of zeros of certain polynomials in the matrix entries, which is also the set of zeros of a collection S of polynomials in the matrix entries of Xij, and of course this is also considered a polynomial function on GLN. So, so one says that G is defined over Q if you can take the set of polynomials to have rational coefficients. If S may be chosen here. So for example, the kind of groups which we will look at are SLN, sp2g, and so on. And just to be clear that there are groups which are not defined over Q, I could look at this quadratic form in n variables where this pi is so if you take the group which preserves this quadratic form, that's not defined over Q. So now suppose gamma is a subgroup of GL and Z, that is n cross n matrices whose determinant is plus minus 1 and which has integral entries. So I could look at the Zariski closure of gamma, that's G, that's automatically defined over Q. It's a small lemma. G is defined over Q. So one says, this is a definition which you have heard about 1,000,000 times by now, but I'm going to recall it anyway. One says that gamma is an arithmetic subgroup if gamma in G of Z, which by definition is the intersection of G with GL and Z, has finite index. So actually this is a relative notion. It's gamma, for example, could be a free group, which is certainly a congruent subgroup of level 2 and SL2Z, but it could sit as a thin group in GL and Z. So it's really, when I say it's an arithmetic group, it's not an abstract arithmetic group, it is an arithmetic subgroup in this sense. So it's a relative notion. So the issue is otherwise gamma is thin. Is whether a given finitely generated subgroup of GL and Z is an arithmetic group or not. Oh, by the way, there is a result which says that all arithmetic groups are finitely generated. I think that's a result due to Borel-Harishchandra. Okay, so what we want to understand is whether a given finitely generated group is an arithmetic group or not. Can one tell if a given finitely generated gamma in GL and Z is arithmetic or thin? Apparently in this general it's not a decidable problem. I don't even understand what it means. So but in any case, so you can certainly agree that it's a very difficult problem. So a more tractable problem is whether groups which are sort of occur in nature, whether they are arithmetic or not. So one of the groups which occur in nature are the so-called monodromy groups. So the question that one wants to know is whether monodromy groups which are very naturally defined, which can also be adjusted to be inside integer matrices, whether they are thin or arithmetic. In fact, in such a context, there was an old conjecture by Griffiths and Schmidt which said that all monodromy groups should be arithmetic. This was in 1971, and counterexamples to these conjectures were constructed by I think Picard in 1871. So let me first define what a monodromy group is, but in a very limited context.
Will you at some point write down the history of it?
I don't think I should do that. Yeah, I don't want to embarrass people. Oh, the Picard example. Yes, I will mention something about that. Yeah. Yeah, so I will define monodromy groups in a very simple context, namely the context of linear differential equations. And talking of historical context, my source of information is Alphonse's book on complex analysis. According to him, this was the first occasion on which the concept of monodromy was introduced by Riemann. So what is the situation? So let's look at U, a connected open set, in the complex plane. So it has some homology, maybe some punctures and so on. It's I didn't mean to be so picturesque. Yeah. So now I will fix functions from the open set to C which are holomorphic. So I want to look for solutions to a linear differential equation with coefficients in this which in all these FIs. So I'm going to look for solutions to this linear differential equation. So this is a linear differential equation. So if y1 and y2 are solutions, their sum is a solution, and the linear combination is also a solution. So the solutions form a vector space and we would like to understand what happens to these solutions if I move around the loop and come back. So whether I get new pairs of solutions, so that's the question. So the action of the space of loops based at a point on the space of solutions is exactly the monodromy. So to define this precisely, let me recall a result of Cauchy. So now suppose my open set is the unit disk. And this Fi is holomorphic. So you can always find solutions. They can be completely specified once you the only arbitrary thing is their first n-1 derivatives. The value at 0, the first derivative at 0, and so on. If those are specified, then the solution is completely determined. Then the differential equation has n linearly independent solutions which are determined, each of which is determined completely by their values. Call this y one of these. So the proof, of course, is actually rather obvious. What you do is solve for this differential equation in formal power series, which you can do. Then you will find a recursive relation for the coefficients. And this recursive relation, actually you can show that the corresponding formal power series solution converges in a small neighborhood of 0. So it converges. So that's the proof. So now coming back to this general equation, I fix a point, let's say P, and move around this. Then you can cover this loop by small disks like this. So on each of these disks, I can solve this differential equation. I get these local solutions which are linearly independent. And on the contiguous disk also you can find n linearly independent solutions. And therefore on the intersection, these two linearly independent solutions differ by a linear transformation. So each time I move from one open set to another, I have a linear transformation relating the two solutions. And I keep doing this and come back to the old point. I get a new solution, which is of course a linear combination of the old ones. Right? And it's clear that if I deform this loop a little bit, the new solution doesn't change. So the solution depends only on the homotopy class of the path of this loop. So if we traverse around a loop based at P in the open set, then the loop gamma gives a linear transformation okay, and this T gamma depends only on the homotopy class of map of the loop around this P. On the homotopy class. And it's also clear that if I take a loop, go around one loop and go around another loop, I get a new solution, and the new solutions that I get will be product of the two old linear transformations. In other words, we have a homomorphism rho from pi 1 of this connected open set into GL and C. Called the monodromy representation. Of the differential equation in question. So the image of rho, which will denote gamma in say GL and C, is called the monodromy group. So this is what we want to understand. You know, you start with a differential equation like this, you get a subgroup of GL and C, and under what conditions can you say that you have an arithmetic group here? So actually it's a very difficult problem to determine even in very simple cases when the group gamma is discrete. That's already quite tough, and in fact there is a paper by Schwartz where he determines this for some very special differential equations on P1 minus 3 points, the hypergeometric equations, when the group is discrete, and whenever it's discrete he is able to show even that the group is in fact a lattice in a certain unitary group U2C. So much for this general theory. So let me just maybe I'm going a bit slowly, but yeah, let me just take up one example before stating the general result. So I'll take U to be the punctured disk. That is that disk so just to before telling you the general result, let me just give you one example. I'm going to look at this differential equation right, where alpha is a constant. So you can of course solve this. This is y equals z to the alpha, but of course this solution doesn't make sense because it's not a function at all. It's a multi-valued function. If you want to think of it as an actual function, you want to view this as a function on the universal cover. So we have this map from the upper half plane into del star, which is tau going to z. So if I have this punctured disk, and I have this loop here, the generating loop, that just is when you view this fundamental group as a covering transformation, it just takes tau to tau plus 1. Right? So this is e to the 2 pi I alpha of tau, and so the generator of this fundamental group just takes tau to tau plus 1. So the new solution is e to the 2 pi I alpha tau plus 1. Therefore, it is e to the 2 pi I alpha times y. So, for example, this differential equation, so the monodromy representation is just a homomorphism of z into C star, and that homomorphism is simply given by taking the generator to e to the 2 pi I alpha. And if you are interested in the question, when is the monodromy finite, this just says the monodromy is finite if and only if alpha is rational. So that's the same thing as saying that the solution to this differential equation is algebraic if and only if alpha is rational. So this sort of thing was mentioned by Peter. So while we are about it, let me just take up just one more example. So here it's clear that if I take y to be constants, nothing happens. Y equal to 1 is a solution. Y equals log z is also a solution, because if I differentiate log twice, I get minus 1 by z squared. That's also the right hand side. So y, I'll instead of writing log, I will write tau, because log z is 2 pi I times tau. And again, the monodromy takes the constant to itself and tau to tau plus 1. So in here, the monodromy the matrix is just this guy with respect to the basis 1 and tau. So whenever you have these log singularities, you should expect a unipotent group. Whenever you have this kind of singularity, you expect a semi-simple element. So this the notion that I want to talk about is important for what follows. So let me say it. So now suppose that yeah.
What if alpha just is not real?
It doesn't matter. It doesn't matter.
It's a bigger.
It's a bigger thing. Yeah, it's not finite.
So discrete. Like, I thought you said that monodromy was nice if it was discrete, not if it was finite.
No, no. The question is here: when is the monodromy finite?
Is monodromy finite? Oh, not
Yeah,
discrete.
yeah. I was not talking about that question. Yeah. I mean, that question is for a different context. I might not come back to it actually. Yeah. Okay. So I have this thing. Now I'm going to look at the punctured disk again, but look at some very special differential equation where these FIs all have at most a simple pole. So again, U is the punctured disk. Right? This is 0, but I'm going to assume that all the FIs have at most a simple pole at z equal to 0. So here I will simply give the result. You want to understand what happens to the monodromy, and here when none of them has a simple pole, you have all solutions which extend to the puncture as well, right? If all the residues are 0, by Cauchy's theorem, all the solutions are holomorphic everywhere on the disk, including at 0. Therefore, the action of the monodromy is trivial. But if I take all the to be pole, then you don't quite get this result, but you get almost the same. Then there exists solutions yn minus 1 holomorphic at 0 as well, and the last solution is in general not zero. It will have some sort of singularity, either this sort of singularity or the logarithmic singularity is singular. Okay, so what does it mean in terms of monodromy? It means that the monodromy matrix acts trivially on this, because if I have a function which is holomorphic around 0 and I analytically continue this along this loop and come back, because it extends to the puncture, the solution does not change. So all the yi's are fixed under monodromy. So the monodromy matrix T is of this form. The last one looks like that. So this matrix has the property that its identity on a codimension 1 subspace. So such a thing is called a complex reflection. So the differential equations that are bit tractable even on this punctured disk are what are called when the differential when the point 0 is what's called a regular singular point. So let me just state this. So general differential equation for delta star. So I'm going to assume again I have this differential equation. But now assume Fn minus 1 has at most a pole, Fn minus 2 is regular So they have a pole of order at most 2, 3 and so on. So in such a case you can say what the monodromy matrix should look like. So in general this monodromy matrix will look like this, z to the beta 1, excuse me. If all the beta i's are such that their differences are not integers, then it's actually diagonal. In case they are not integers, you will get some unipotent stuff. Okay, so that is how the monodromy matrix looks like. So instead of saying what the monodromy looks like, I could say what the solutions look like. They look like z to the beta I times holomorphic at 0. So this is the only singularity that's that would come. So the differential equation which I am going to look at, it has already been mentioned by Peter before, is when the open set is the plane minus 0, 1. So in other words, I have this projective line. I take away 0, I take away 1 and the point at infinity, and the loops around 0, the loop around 1 and the loop around infinity generate the fundamental group, but they don't generate it freely. There is a relation. Phi 1 of u, let's say at half, is h naught, the free group generated by these guys, okay. So the differential equation is what's called the hypergeometric equation. So let me introduce the following operator. Theta is z d by d theta dz, sorry, and I fix numbers. So this differential equation is a one variable differential equation which depends on these two n parameters, theta plus beta 1 minus 1 So that is our differential operator, and we are looking for solutions to this differential equation. So if I apply this general result about the punctured disk to this equation, but concentrating my attention on here, the matrix around 0, so call this matrix B inverse. So in general, B has eigenvalues for some technical reason one has to write it as B inverse, not B. So the eigenvalues of the monodromy matrix around 0. So in other words, the loop around 0 goes to a matrix whose eigenvalues look like this. These betas are here, and the monodromy matrix A around infinity has eigenvalues exponential of these things. So all that one is saying is that the solutions to these differential equations have a certain kind of singular behavior at 0 and infinity. Okay, but let me write out this differential equation at least for z equal to let me just look at the nth order term. I have z d by dz here, z d by dz here, and so on. So the highest degree term looks like z to the n plus lower degree polynomials, and here I have the same, except that the highest degree term is a bit more. So this is z to the n 1 minus z some polynomials. So this is exactly the situation for monodromy around 1, that almost all solutions are holomorphic at 0, because all the coefficients will have at most a simple pole at z equal to 1. So I have the monodromy representation rho pi 1 of into GL and C. It has the following properties: the loop around 0, its inverse, its characteristic polynomial, the loop around infinity has characteristic polynomial, and the if I look at H1 rho H infinity inverse rho H naught, so it's called, it's A inverse B. This is a complex reflection. So that's because of this. But if we are given this much information, it completely characterizes this representation. There is only one representation up to conjugacy satisfying all these properties, with a small assumption. Excuse me? The characteristic polynomial. Excuse me. So a theorem of Levelt tells you that such a representation is uniquely determined up to conjugacy. So let me state the result. Assume is not an integer for all jk. Then first of all, so the image, we had denoted the image of rho to be gamma. Then the monodromy action acts irreducibly on C to the n. There exists one representation. So given arbitrary betas satisfying these conditions, there is always a representation with these properties rho naught, such that B has characteristic polynomial, has eigenvalues alpha j, and A inverse B is a reflection. And all such representations are conjugate. So this is actually part of a very general result due to Nick Katz. He calls this a rigidity theorem. So given this, you can forget entirely about the differential equation with which he started. We just want to concentrate on a representation which has these properties. So let me just show you how this rho naught is. It's very easy to describe. So if I have a polynomial f of t not, I could look at this ring f of t. This has basis, and the multiplication by t operator has a certain matrix which is multiplication by t, just looks like this. This is called the companion matrix of F. Companion matrix. So what you do is to construct this representation, you take B to be the companion matrix of G, A to be the companion matrix of F, where F is T minus e to the 2 pi I alpha j, and G so you have just two matrices, namely the companion matrices. You take the group generated by them. This is called the hypergeometric group. So various questions arise. When is this gamma a discrete group? When is it a lattice? When it's an arithmetic group, and so on. So that's the kind of questions which you want to understand. And it seems very likely that most of the, if you arrange matters in such a way that these gammas already lie in GL and Z. That's very easy to do. You just choose polynomials whose coefficients are integral, but of course you have to make sure that this has determinant plus minus 1, so A naught is plus minus 1. So we will assume, for convenience, f of 0 is 0 or plus minus 1, f g or polynomials of degree n, and this condition really means that f and g have no common factor. F g coprime. So the group generated by this A and B is now a subgroup of GL and Z, GL and Z. So that's the question. When are these hypergeometric groups arithmetic groups? Is there a criterion to tell whether it's a thin group or not? Okay. So let me just mention the result. Peter had already done this.
So is it automatic that then A inverse B is a reflection?
Yeah, because these two are companion matrices. So on the first n minus 1 basis element, they have the same shape. Yeah, that's a point. Yeah, you see, they are companion matrices. So the first basis element goes sent to the second, and so on under both. So they are equal on the first n minus 1 basis. I'm sort of run out of time. May I take 2 more minutes? Oh, there is still 2 minutes actually. Okay, so but you see, for reasons coming from geometry, these monodromy matrices should not just be arbitrary numbers, but they should be roots of unity. If you are interested in a situation where this is actually a geometric monodromy group, I haven't defined that, then we will restrict to the case when alpha, beta are rational numbers. So all the roots are roots of unity. So that's the same thing as saying that the companion matrix has the property that some power of it is unipotent. So such a thing is called a quasi-unipotent element. So we want that the local monodromies should be quasi-unipotent. So I'm going to assume all this. They have integral coefficients, they are monic of degree n, and the zeroth coefficient is plus minus 1, and the roots are roots of unity. In other words, f and g are products of cyclotomic polynomials. But you somehow this much information is enough to tell you what the Zariski closure is. It's quite an amazing result by Beukers and Heckman. Somewhere in invention is 89, I think. So let me take G to be the Zariski closure of gamma. And I'm going to make one extra assumption, which is, so I should have mentioned this, f, g are primitive, i.e. There does not exist a k such that f is composed with t to the k, and g is also of the same type. You can't have two polynomials like this. If you had them, you call them an imprimitive pair, and you want to assume that they are primitive. Either the Zariski closure is finite if G0 and F0 have the same sign. Actually, you can assume plus 1. Then the Zariski closure is a symplectic group. N is necessarily even in this case. If they have the opposite sign, then the Zariski closure is the orthogonal group. So the issue here is you have this monodromy group, whether this is a finite index subgroup or not of the integral symplectic group or the integral orthogonal group. So I will come back to this example, but let me mention this. This was proved quite recently. If f is x to the phi minus 1 by x minus 1 and g, so these have no common factors, they satisfy all these conditions. Okay. So the value at 0 is 1. So the Zariski closure is a symplectic group. For Z, this is Zariski dense, but this is thin. This has infinite index. What they actually show is that the group which is generated by A and B is in fact A has order 5 and B has order infinite order. It's a unipotent element, and it is a free product of Z5 with Z. If it were to have finite index, then the abelianization of this would be infinite. But one knows that for arithmetic subgroups of SP4, the abelianization is finite. Okay, it follows from Kazdan property T, for example. All right. So this is a thin example because they actually physically show, using some sort of a very fancy ping pong, that the group generated is a free product. So this is not known as far as I know. If I take x to the 7 minus 1 by x minus 1, g is x minus 1 to the 6. This is also what Peter mentioned as the monodromy associated to the Dwork family, but one doesn't know this. So let me just mention one result, which is also, if